So now this is fundamentals of spatial filtering. So an image is to be smoothened, or image has to be identifying the particular part of the image. In order to identify a particular part of the image, if it is hidden on the background of darker shades or the more brighter shades, the image enhancement process is required. So then this spatial filtering is done on those images. So let's look at the spatial filtering methods. So we use this, there is an image, entire input image is there. It is done by pixel. The changes, the filtering mask is applied for each pixel of that particular image. So that means if this particular pixel has to be changed to filter it, if this particular pixel has to be changed to filter it at this particular point, okay, at this particular point, and it is corresponding one function transfer T is applied to the neighborhood pixels. So the T is and operates on the neighborhood pixels of this entire, about this neighborhood pixels in the sense this pixels, entire this pixels, and this pixel, and then its reassigned value is comes into the output of image. Like this, for every pixel, the neighborhood values are considered, image values are considered, and then the new x of g axis of value is reassigned to the output image. That means it uses neighborhood, which is the pixel process, and then operation on that pixel process gives us the necessary filtrations, in the sense, it will either flap the image and then apply on that masking. Okay, so entire matrix is blast and then applying the matrices, or directly it could be applied on the matrices of the image. That means, for example, usually it has taken a shape of k by k. So we call it as a window of that particular area of that pixels. If this is the darker shade of the gray, is the area of the pixel which is to be filtered. Means each pixel is considered. This is spatial domain. This is applied to it. As spatial domain, we know that it is done applied on the pixel by pixel. Spatial domain is there are two types of image enhancement methods: frequency domain and then spatial domain. So this is spatial filtering, which is a spatial domain enhancement image processing. So that means it goes with pixel by pixel transformation of images, enhancement, to get an enhancement in the image. Say this is an area of the pixel, for example, in an entire image FF, this is the particular pixel. So like this, each pixel is considered. Its neighbor, if you take that will become 3 by 3 3 by 3 scale window, 3 by 3 scale window, or means matrix of 3 by 3 for f of x, that is for x and y coordinate of that particular. So it could be like 5 by 5. It has to be m and n has to be an odd number here. It can be like a 3 by 3, 5 by 3. M and n has to be a odd number. Then a new value is produced by processing that window pixel like this. So this is an image, this is the gray values of that particular image. Okay, so if Z5 has to be translated, okay, Z5 has to be filtered in the operation, then it becomes Z1, Z2 or Z1, Z5. These are the function operations which is applied on it. Okay, so let's consider there are two methods in this, linear and then non-linear filtering methods. So linear method is a product of sum and non-linear method is maximum of that value, whatever that entire square matrix is there, no. So this is applying product of sum of products. This is one linear method. In non-linear method, that entire image, that is the Z1, Z2, Z3, Z4, Z5, Z6. So this is input image entire. The mask is used as to find the maximum of that and then use it with the mask. So these are the two methods we can call which is used for spatial filtering, linear and then non-linear. In linear, we have two operations. In linear filtering, we have two operations. One is correlation operation, another is convolution operation. So, there are two operations are done in order to get linear spatial filtering. One is correlation, another one is convolution. Okay, to get a linear combination output for the input images. Okay, so let's understand what is correlation linear operation, how this filtration is applied. So for the correlation output image for any input image, that each input pixel it will be weighted sum of products. Okay, weighted sum of products. So something like this. Okay, so Z5 is okay. So Z5 is, let me take a pointer brush here, highlight that. Okay, so if this is the linear, this is the neighborhood. Okay, so this is neighborhood and Z5 is what is to be calculated. So we use Z5 as new Z5 dash is calculated by weighted sum of products. So W is a window. So this is this is known as a mask window. So this is weighted a mask window and this is applied on this each pixel value, that is a gray value of that particular pixel applied on that, and then you getting the new Z5 value. So let's understand with an example of that. Okay, if this is an input, there is a kernel mask of that is applied on the actual image. This is actual image pixel and this entire mask is applied on that to get the neighborhood this pixel. So like this, the array of each pixel is applied on the array of matrix, that is the kernel matrix, that is masking matrix, it's also known as masking matrix, is applied on the each pixel of input image and its corresponding output scaling of constraint you get for every pixel of that. So let's consider how it is done. That means the new value will be for this is sum of the neighboring A and B are the masking values, and then it's x of t and then y of x of s plus y of t. So its product is what we get, a correlation new value for the output image. Let's consider. Okay, so that image is directly taken. Now correlation matrix, this is our W correlation matrix, K by K. So always I told you it has to be in the odd number, either 3 by 3, 5 by 5, in that range. Okay, so if taking this as a masking table, and this is the input, so 2 3, these are the gray levels of that image. Okay, of a particular, say if there is an image of 4 by 4, so this is the image value, pixel value, this is another pixel value, this is another 2 2 2 3, these are the pixel values, 2 1 3 3, these are the pixel values of image F, input image F. And this is our masking 3 by 3 value, masking kernel value is called. Okay, so when it has to change the pixel value of this first pixel, okay, to change the pixel value of 2, okay, how this entire table is applied. So it is just taken overlapping on that. So considering for the 2 here, for the 2, the neighboring pixels are 2 1 2, isn't it? These 3 are the neighboring pixel of this. So we want to change, we want to look for the correlation value of this particular pixel, changing it for the output image. So for this 2, the neighbors are 2 2 and 1. So it has this neighbor that we studied. When the other neighbor is not there, it is considering it as a 0. Okay, these values will be considered as 0 only. Okay, now putting this mask, whatever the kernel W mask is considered, that is 1 minus 1 1 2 minus 1 1 1 1. This is a 3 by 3 mask matrix is considered with the value. There is some function is to be applied on it. Then it just placing this above this here. Okay, it just consider when it is placed above here, what happens? 2 plus 2 is 4, minus 1 into minus 2 is minus 2, 1 into 2 is 2, 1 into 1 is 1. So what happens in this matrix is that entire this is added sum of this. Okay, after that you get a square matrix value, then have a product of, then summing 4 minus 2 is minus 2, 2. Okay, 2 plus 2 is 4 plus 1 is 5. Then this becomes the new image correlation value 5. Hope you got that. You are getting 2 into 2, sum of product. Okay, sum of product, because this is 0, no, here this is 0, the other part of this matrix is 0, isn't it? So this all term will become 0. Then now 2 into 2 4, minus 1 into 2 is minus 2, 1 into 2 is 2, 1 into 1 is 1. Now we'll have adding up. Okay, minus 2 minus 2 is 0, 4 plus 1 is 5. So when you sum up all these 4 values, you get 5. So the 5 is the new value for the replacement of this pixel. Similarly, another value for this. Okay, for 2. So for 2 to be a middle, its neighbor pixels are 2, 2, 1, 9, 3 and 2. Then apply the mask on that. So the same way, it is 2 into 2 and this summing up you get 10, isn't it? Okay, so this means to say this, the 2 rows will sit on this. Okay, 1 into 2 is 2, 2 into 2 is 4, minus 1 into 2 is minus 2, 1 into 2 is 2, 1 into 1 is 1, 1 into 3 is 3. Now summing up of all this, what do you get? 6 minus 2 is 4, 4 plus 2 is 6, 6 plus 1 is 7, 7 plus 3 is 10. So we get 10 as a new value for this corresponding input image 2 at this point. So this is our output matters. So similarly for the next. So it gets applied like this. So this way each pixel value is calculated for the input image each pixel value. So each pixel values are nothing but their gray levels. Okay. So this how this again the corner. This how the entire image values are calculated. Then we get that output final image of that correlation image. Okay, correlated image. So after calculating this correlation, that image is displayed, which would enhance the quality of that image. Either it will blur that other highlighting parts, that is brighter parts, and with that blurred brighter parts, the edges are identified, as well as that hidden images on the under the darker parts will be highlighted. Okay, so using this correlation linear spatial filtering, so image enhancement is done. Okay, so this is what the neighboring would be getting as a boundary levels will be padded up with 0 for any values. Okay, so how does it happens? Like template smoothing, similar image. See, like for V, which is not exactly like a V, will become like this. Okay, correcting its edges, because we are correcting the gray levels of the neighboring, considering the neighboring pixel value. Okay, that image of this flight, which is of this way, would become this matching. This is how the simple way of doing the correlation. Okay, so now the next method, that is convolution. Convolution is a linear operator. It's a linear operator. Linear operator is a gradual changes into the pixel values. It is similar to the correlation, except the masking is flipped both horizontally and vertically. That means that entire masking, what the matches we get, we split it both 180-degree we can call. So once horizontal flipping and then vertical flipping is done to it. So thereby we get vertical flipping is 90-degree, then horizontal flipping another 90-degree. You get entire image in that flopping mask is into 180-degree shift. So after doing that, it is applied to the matter. So it is again the sum of products. Okay, so only thing is here, in a correlation method of linear operation, it is directly applied, whereas in convolution method it flips both the side, vertically and horizontally, so that you get 180-degree of change into it. Okay, so it is symmetric than the equivalent to correlation. Okay, so it's again the convolution expression, that is sum of, this is where a and b are the constants. Okay, so constant in the sense whatever the neighboring, that is m and n values we are getting that. Okay, so now applying correlation to this value. Okay, so let me take the point. Okay, So here this is the which is the pointer ink to okay fine. So this is our convolution kernel matrix. This is a masking. This is our masking matrix. Okay, so it is rotated to 180 degree. So you're getting it. First is horizontal flip, then vertical flip is done. So it will become one, the rows will become column, all the column will become into rows. So sorry, when it is flipped, all the rows will become into column, column will become into row. So 1 1 1 becomes a row mat. Minus 1 2 1, it will become a row. Minus 1 minus 1, it will become a row. So this rotated one is applied on the entire input image F. Just like we got a transformation of each pixel in correlation, here convolution is done after rotating that mask window matrix. Okay, so the same way this is also applied here for this input image. Now this should become our new matrix, that is the masking matrix. Okay, so in this masking matrix, again the similar way. So this is applied 4, output image value you get as a 4 because 2 into 2 is 2, 1 is 2, minus 2, 1, you get 4. Whereas there it was 10, now it becomes 4 because minus 1 into 2 is minus 2, 2 into 2 is 4, plus 1 into plus 2 is 2, minus 1 into 2 is minus 2, minus 1 into 1 is minus 1, 1 into 3 is 3. So thereby when it is summed up, get 4. Okay, minus 2 minus 2 0, of course. 4 minus 2 is again minus 2, minus 2 into that's what you get as a 4 in the output. Okay, so the convolution is nothing but after flipping that kernel matrix, this operation is applied on that 3 by 3 matrix. If it is 4 by 5, it will take all the 4 by 5 of that particular corner pixel, centered pixel. So each pixel is calculated. Each pixel is calculated. Okay, see for this, and then for this. So output for each pixel is calculated by masking matrix. You can directly see, you can see then the entire mask is applied on this because it gets that's for this 1. It becomes 6, value 6. Okay, for an input image of that. Okay, this way the convolution new array of image matrix we get after convolution expressions are applied, operations are applied on it for each pixel. Okay, so this will give a new image for that input image, which is linear convolution converted or translated or enhanced image. Okay, so this way, for example, this is the original image. Okay, original image. So the W 1 2 3 4 5 is 1 2 3 4 5 is our okay So 1, 2, 3, 4, 5 is what is our masking values. It could be anything, masking values. So original image has only one bit here to be transferred, and padding up with all the full screen. See, it will become like this. 1, 2, 3, 4, 5 with the 0, 1, 2, 3, 4, 5 with the 0. As it is corresponding, correlation becomes like this. Then cropped, what is it? Convolution, because it is rotated. When it is rotated, you get back to the same, isn't it? Okay, are you finding the difference of that particular pixel? All its neighboring pixel would alter to its value. Okay, so this is what corresponding correlation comes like this, whereas in correlation it comes like this. It flips, and here it is flipped. After that you're getting an original. Okay, so these are the two methods used for linear filtering, that is spatial filtering in the image enhancement process. Okay, so now filtering has two categories. One, two, for low pass filtering, it's also called as smoothing of the image. Smoothing of the image. For smoothing, it's called a low pass filter. Another one is sharpening of the image. Smoothing in the sense where every edge is corrected, and then gray levels are like histogram equalizers, like gray levels are uniformly distributed, whereas in the sharpening, the high pass filters, it is also called high pass filter, the image contrast and brightness is enhanced, changed. Okay, so in a smoothing, it reduces the noise and then removes the small details. That elements of the mask has to be the positive, that is Gaussian mask. This is a Gaussian mask, 7 by 7. The element sum of 1, assuming to be normalized weight, divided by each weight of the sum of weights. So this is again calculated through the image uh, levels, for every pixel image levels. If it is 7 by 7 mask, or a 3 by 3 mask, or 5 by 5 mask can be applied on each pixel. This is example of Gaussian mask of 7 by 7. Okay, so the image smoothing. So if this is an input image, the smoothed image would be like a blur way. It will highlight the inside images. Okay, inside images. Okay, so sharpening filters are high pass filters. They are very useful in highlighting the brighter parts and contrast part in the image. Okay, so the mask is applied both in negative weightages as well as in the positive weightages. So here in smoothing, only positive weightage is applied. See the mask. See the mask value, there is no negative in it. There is no negative values in it. So all the mask value elements has to be positive, whereas in sharpening it can have both positive value as well as negative value. That entire sum, only thing is entire sum of the mask is equal to 0. Entire sum of the mask is equal to 0. Because when you sum of all this mask value, it becomes 0. It is a combination of weighted combination of positive as well as negative numbers. Okay, so for sharpening purpose, that image is applied like this. So this is the mask of that particularly 3 by 3 mask, and on the image it is applied like this. Okay, so this is 1 by 9, 9 elements are there, and this is weighted sum of the products. There's no variation in the grayscales in this. Okay, there's no variation in the, there is a variation in the grayscale. Okay, in this mask. So in this mask, there is a variation in the grayscale, whereas here there is no variation in the grayscale. Okay. So this, the sharpening filter, if this is an input image, see the better visualization is given when the sharpening is added to it. Okay. So because of that, the image clarity is enhanced. So this is what is sharpening filter applied on the image enhancement methods. Okay. And there are common smoothing filters are there, where we use average linear method, Gaussian linear method, and then maiden filtering. This is applied for the non-linear. There are two spatial domain methods are there. Both will have a smoothing filters, non-linears as well as linears. Okay, in linear, averaging is done, Gaussian method is done. In non-linear, maiden filtering is applied for smoothing. Okay, so smoothing filter of averaging is nothing but if there is a, this is 1/9 of it. Okay, and this is 1/25 or 1/49, because it's always in the odd numbers. Smoothing matrix averaging is done to each. So masking values, this becomes our masking value into 1/9, and that is applied to for each every, that is if 3/3 is applied, that image would be like, see 5/5 is applied. See, as more the degrees you get the blurrer images, more the degrees you get blur image. That means that blurring that particular area of the image using this smoothing filter. Okay, so this is averaging. Averaging is again, okay, so this is an image extracted with the largest size, and 15/15 averaging is done on this. Okay, so this is after the blurring, threshold is calculated to it, which will highlight after the image enhancement process. Okay, so now in Gaussian's method, this is actually a positive numbers are only used for as a weighted samples matrix, and this is an image which would have the values, and this is an expression which gives us the conversion of smoothing filter. Okay, 7/7 matrix is an example what is considered here for each pixel masking. Okay, for each pixel masking to find its new smoothing g of x and y value. Okay, so usually the conversion takes like this. The probability of a density increases or decreases according to the value. Okay, so this is applied to the Gaussian masking of 3 and then 7, 15/15. So this is calculated value to this entire smoothing mask. Okay, so when it is applied to that way, the smaller the smoothing blur, the higher the smoothing, strong smoothing is done on the image. Okay, so this is average method smoothing and then Gaussian method smoothing. So this makes a bit of difference. The gray levels are changing into the image. When the image input is this, when averaging is done, average smoothing is done, this is what the image filtration occurs in the image. And Gaussian method is used, then it is 7 by 7 or 15 by 15 masking. Then this is the output image which is getting converted for the further image enhancement. This is a smoothing of image. And next is for the non-linear filters. For non-linear, so there it is maximum products of neighboring. It's called as bringing up into salt and pepper. So actually I hope you are able to visualize. This is salt and pepper. Okay, this is called salt and entire image will be like a pixel. It will be like a distinct pixel. Okay, distinct pixel. This is original image, this is distinct pixel. That is entire image occurrences would be into black and white pixels for effective removal of image. Okay, this is how the image some image pixels are removed and changed into black and white. So this is known as salt and pepper noise removing. Okay, so this is averaging is done like this, and median filtering would occur like this. So it replaces the each pixel by median in the value, in the sense that is a product of every each values and then divided, isn't it? So sort it and then find the median value here. Sort it and then put the median value. Clear? So this is taking the output image of x and y, sorted all the 9 pixels, and its median value is 20, the center value. So it replaces with the 20 here. Okay, the 19 is replaced as 20. The size of the neighborhood control amounts the smoothing. That is, what is the size of the gray values in the neighborhood will be a value for the smoothing filter. Okay, smoothing filter. See, neighborhood values in the image is 10, 20, 20, 15, 99, 20, 20, 25 and 20 here. Okay, so taking all those values, sorting it out. See, it is trying to convert find the value of this pixel which is having 99. And by applying the median neighborhood pixel operation method, the median value after sorting would be 20. That is the middle value. And that 19 would change it into 20. Like this, for every pixel, it will apply a median filtering method. Okay, so common sharpening filters are high boosting filters, gradient one derivative, and then lapsation derivative. Okay, so this is unshaping masking of text 1. You are getting the TEXT text, that is high contrast enhancement is applied for a better visualization. Okay, so subtracting that you get high contrast value. Okay, high boost filtering, sharpening of the image, original, blur, and then sharpening of the image. So this is another example. Original, when the Gaussian method is done, G mask is done, unsharp mask is done. And so the put together 2D example, it is boosting filters we call it. Okay, and it is derivatives are applied on this components. The gradients are changed. Okay, gradients are changed using this formula computation method. Okay, so this is a gradient vector which has a magnitude and then direction. So you would have found like gradual changes from smoother edge to the sharper edge. So the gradient changes are calculated using these methods. Okay, direction is tan inverse of that, and then magnitude is root of that. x and y function with respect to x and y. Okay, gradient magnitude provides information edges in the strand. Okay, and direction is perpendicular to the direction edges. This is how the gradient is calculated for the any image computations. So there is a partial derivatives using the finite differences for any notation of x and y. Okay, so with respect to this, it will calculate new dimension values. So this is t- to this we will conclude the session. The next we will go for, and this is how the each pixel values are calculated for gradation. So visualization partially with the derivatives can be imaged. So like this. Okay. So for derived gradation components, it is implemented dy by dx formulation of the matrix. So this is what the approximation mask is used. Okay, magnitude imaginations, second derivatives,